Yeah, so I think I would definitely want to agree with some of the things we heard here. We have to have fundamental knowledge if we want to understand how this global scale biogeochemical cycles work. And I think I would like to start actually by, by thanking the people that contribute to this project, specifically, of course, to Roman Stoker, which is my previous advisor, and of course to the people who paid my salary in the last few years. So with this, we are ready to start. So large-scale biogeochemical cycles are often catalyzed in the environment by microorganisms. But despite their importance, many times we scientists, we don't know the identity of those microorganisms. We don't know their activity, and we don't know the interaction between them. And I think what I will try to convince you in the next 15 minutes that I have is that studying those microbes is extremely important if we want to understand how those large global scale biogeochemical cycles function. Okay? And what I will try to do is to literally show you, imaging how little microorganisms grow on one of those particles in the ocean. And Chris gave an introduction, and then also Astrid gave an introduction of the biological pump. It's all about those little particles that sink. And what you see here, those are the little bacteria that live on those particles. And as you can see in their environment, they have flow. Okay? So they interact with the physical world. And when I came to the lab, I had this idea, why don't we take a microscope and throw it into the ocean, and then see how those degradation processes work as this particle move into this water. Of course, we didn't got the funding for this because the microscope is quite expensive to throw into the ocean, but I heard that some people are now trying to do that. Okay? So I think I would like to again introduce you to the biological pump. It's very important, and maybe it's good to repeat. And then I will talk about how sinking affects the degradation, and then how biofilm can affect the sinking of particles. So again, the biological pump is the process by which carbon dioxide is absorbed by photosynthetic microorganisms at the top of the water column. Now, as those microorganisms die, they tend to aggregate in several pathways and form this particulate organic carbon, which sink into the deep ocean and carry the carbon assimilated in their biomass to the deep ocean. Okay? Now, it usually looks like this mess, okay? A lot of schmutz, if you want, things that grow and come together, and there is a lot of polysaccharide that hold all together those particles. However, when those particles sink, they are also colonized by bacteria, as we just saw, and they are degraded. Okay, so those particles is a food source for the microbial community that live under in the deep ocean, and so that only 25% of this carbon actually leave the euphotic zone, 1% reach the sediment, and as the deeper those particles remineralize, the more time this carbon will stay under the ocean. In fact, carbon that goes all the way to 1,000 meters will stay there for thousands of years, and therefore the biological pump, as was mentioned, is extremely important to understand if we want to understand the oceanic carbon cycle. So as Astrid already said, 1.5-fold more carbon dioxide if we didn't have the biological pump, so it's extremely important, and we need to study the microscopic interaction that actually control this flux of carbon. So the first project that I would like to focus on is what is going on with the two major powers of the biological pump. So the biological pump, if you think about it, it's two opposing powers. It's sinking and degradation. That's all it is, okay? And the faster the particles sink, the more time the carbon will stay under the water, the faster the degradation goes, less carbon, so quite simple. But when I came and started my postdoc, I asked, wait a second, are those two powers are independent or dependent on each other, okay? So if we take particle, if it sinks fast, does it also degrade fast or slower, or maybe there is no relation between sinking and degradation? So very naive question. So in order to test this hypothesis or this question, what we needed to do is what many people in the lab of Roman Stoker do, is to build this microfluidic system. So what we build is a microfluidic system, which is a particle on a chip. It's a little particle made out of polysaccharide. The polysaccharide is alginate. Alginate is just a polysaccharide made by brown algae, so it's just a model system like other model systems people use. And as you can see here, the particles are quite spherical, and that's nice because we can quantify the degradation rates. It's pretty easy to calculate the volume of those particles. And you can see the little bacteria floating in the surrounding because we introduce flow into the system in order to mimic the sinking of the particle. So now we have a very simple system which we can control the sinking speed of a particle and let the bacteria that live on this particle feel as if this particle is sinking to the water. Okay? So this is an experiment, a long-time experiment. You can see it's a 48-hour experiment, and you can see how the bacteria grow on those particles. They are fluorescently labeled in green, so the little colonies that you see in the surrounding and also on the particle, those are bacteria. Okay? They grow together, they function together, they degrade the particle, and then they, for some reason, escape. Okay? And in the meantime, there is also, we can quantify the particle volume and therefore the degradation rate of this particle. Okay? Just to make sure we understand, it's a particle, little colonies of bacteria, enzymes, they degrade, breakdown products are going into the solution, and then most of the breakdown product actually goes into the sea with the flow, and a little bit is being eaten by the bacteria in order to produce biomass. Okay? So does flow play a role in determining the degradation rate? So we made a simple experiment in which we test the degradation of particles in the presence of flow and in the absence of flow. Okay? Extremely simple, and you can clearly see that with flow, the degradation of those particles made out from polysaccharide is a much, much, much faster. We did the same experiment with many flow rates, which represent the sinking speed of natural sinking speed that you can find in the ocean, although on the low, I would say on the low side of the sinking speeds. And we can find, if you see that's particle volume as a function of time, and we find that the more flow we add, the faster the degradation is. And you can see here we quantify, and the degradation rate is actually a function of a sinking speed. So we could actually find an interesting and a fundamental relation between the two powers that drive the biological pump. We call this fundamental relation the sinking enhanced degradation. And what we want to do is to understand what is the mechanism. Why is this the case? Why is sinking enhanced the degradation? So we came up, we tried several things, and the thing that came out is pretty simple. So I'm a biochemist in training, and biochemistry, again, pops out just like that. So what we see here is a particle which is exposed to the breakdown products of the degradation. Okay? And what we found is basically a situation when we produce the product, it inhibits the activity of the degradation. So this is a product, product inhibition, which is well known in other systems. And without the product, the degradation is fast and normal. So if you want to see, the more byproduct we add, the slower the degradation, and we can have this inhibitory curve that I did, and you can see that already a very low concentration of the breakdown product can inhibit the activity of those microbial community. So the hypothesis we have is quite simple. In high flow, the alginate lyase enzyme can degrade the particle because the flow will take all the time the products, and therefore there would not be any product inhibition. On the other end, so low flow, the byproduct will accumulate in the environment, and therefore we will have this, as you can see, a product inhibition, which basically the enzyme will work harder and harder to break the oligomers instead of breaking the alginate particle itself. Okay? We also went and tried to take this microscopic observation and try to see whether we can say something about the environment. So what we did, we designed a mathematical model where we take into consideration the sinking, the growth, and the degradation. And if we put all the ingredients together with the sinking enhanced degradation, we can do something quite remarkable, in my opinion. We can restore the shape of the biological pump. Okay? So for many years, people are trying to model and to try to understand why this is the shape of the biological pump. This is vertical carbon flux as a function of depth. And now we have a mathematical model, and we understand the bits. We understand what are the things that control this degradation process, and we can describe quite nicely what is going on in the ocean. So we could first restore the shape of the carbon pump, and another thing we can do, if we get rid of this sinking enhanced degradation, what we get is a carbon pump which is no longer functioning correctly. Okay? So up until now, I showed you that sinking enhanced the degradation by bacteria, and now I would like to show you that actually bacteria can also affect the sinking of particles. Okay, so in order to test how bacteria affect the sinking of particles, what we did is develop a new macrofluidic system. This is the endless ocean column device. It's a little particle that sits inside a glass column. Okay? This particle wants to sink down, but what I did, I put a camera in front of it, and I designed a loop, a real-time image analysis loop, which adjusts the flow according to the sinking speed. And therefore, what we could make is we keep the particle in the center of the observation chamber. Okay? And we can let the particle then sink to the deep ocean as much as we want and observe what is going on with those particles, kind of throwing a microscope into the ocean if you want. So here's a case when the system is off. You can see the particle just goes away, and this is the same particle when I turn on the system. You can see the particle is now sinking in the center, it goes up and down, and what controls is just the flow. In order to identify what bacteria can actually do to this sinking speed, we needed a model system. So we chose the Altromonas, which is quite abundant heterotroph bacteria that was isolated from one of those particles. And the special thing that this microbe is doing is basically making those biofilm network that you can see here in this SEM image that we took. Okay? So the question is, what would happen if a particle would move through this network of polymers that those bacteria make? Okay? So the first experiment is the control. What we did is to take one of those particles and let it sink in sterile seawater. And as you can see, the particle can sink, and we can measure the sinking speed. And as you can see, nothing happened. The particle is rotating for some reason, and the sinking speed stays quite stable. However, what happened when we introduced the bacteria into the system, then the story is a little bit different. As you can see here, the particle, first of all, slowly is slowing down, okay? And at the same time, there is accumulation of biofilm on the periphery of this particle, as you can see here, and we call those tendrils, we call them biofilm parachutes. And basically what those parachutes do, they slow down, in fact, by 50% within 1 day. Okay, so within 1 day of sinking, the particle was slowed down by 50%. And this has implication for the environment. It means that if a particle is sinking through ocean that contains a lot of bacteria, this will slow down their sinking and therefore will slow down the flux of carbon to the deep ocean. So we find another role for bacteria and gel, which is very important. We are the first to observe it, and I showed it to many oceanographers, and it's very interesting, and many people are now trying to understand how is it working, how many gels we have, where do we have a lot of gels, what would happen in future ocean scenario? Would we have more gels or less? So all of those questions are now slowly we start to tackle them, and that will be one of the goals of my future lab. Okay, so here is the same experiment done several times, and you can see there is about 1% reduction in sinking speed per meter, so I would say quite impressive. And we can do the same experiment this time in bulk. So if we take particles that incubate with the bacteria and particles that without the bacteria, just naked particle, you can see that we get similar results, so it's about 20% reduction in sinking speed. And again, this means we have something, a new phenomenon which is just discovered, and we want to explore it further. So the theory is basically quite simple. In the top of the water column, those gels serve as a glue that takes those particles and glue them together, and basically helping to transform this carbon into the deep ocean. So quite positive. However, once those particles start to sink, they start to accumulate in the form of these parachutes. They change the density of the particle and the hydrodynamic resistance and inhibit the sinking of those particles. Okay? And I hope that I convince you that by studying the microscopic life of those microorganisms, we can also understand something about their environment, and there is a lot of room for collaboration and to start to think about how to upscale this. And with this, I would like to thank you very much, and I will end here. Thank you.
Wonderful talk, Uria. Fantastic.